Yeah, thanks a lot for the introduction and for giving this opportunity. I know this will be a relatively more technical talk, but I'm grateful to Rebecca for the nice introduction that she has done with nice visualizations as well. So when she arrived at the cake, where with the most important parts, and then in the cake she was pointing out at the air pollution side. I'm looking at the water resource management side. Okay, so that's going to be my focus today. So why? Well, I mean, I don't think I have to convince you about the importance of the issue. We know that the agricultural sector accounts for about 70% of use of freshwater resources. And out of these 70%, 86% is due to irrigation. Okay, so sustainable irrigation has a dramatic impact on water availability and the hydrological cycle at large. And clearly this causes groundwater depletion, and this may lead to food and energy shortages, as well as soil salinization and seawater seawater in coastal basins. Okay. Yet, when we think about irrigation protocols that are applied, they're based on heuristic approaches that determine what is the right timing and amount of irrigation. And I mean, that's quite natural, right? Because it's not something it's not something new. We've been using irrigation for thousands of years. So we have a very large bulk of expert knowledge of both agricultural and technological issues about this issue. Yet, very seldomly we apply proper mathematical modeling, or if you want, understanding of the dynamics taking place there to optimize the irrigation cycle. Okay, and I mean, this is even more important if we think about more controlled frameworks where we might grow and harvest produce. So, for example, I was recently reading a tomato grown in the Netherlands with very advanced and highly controlled setting needs 3% of the water of a tomato grown in the US on average. Okay, so it's not just about it's not just about being a rich country or a poor country. It's more about we have a certain amount of information and knowledge. Do we want to apply this, or we want to keep doing things as we've been doing for thousands of years? So this is also in line with what popped up yesterday in the plenary of Sarah Burke. So we have the tools. Are we willing to transfer these tools and make use of them? Okay, so yeah, this is basically for part of the motivations that somehow steer our interest in this problem. So the idea is to reduce the water resource for irrigation, and this also avoids aquifer overexploitation, as well as reduce the risk of soil salinization in coastal areas. Okay, now for doing that, we'll use a highly technical mathematical model that I introduced here. So it's a model that we use to describe the water vertical infiltration, percolation, diffusion in soil into unsaturated zones. This is a Beckman diffusion equation known as Richard's equation. It has been somehow validated over the last 3-4 decades, I would say. Is a nonlinear partial differential equation that describes the the evolution of the, well, either the pressure head, H, or the water content, theta, that is also called the moisture, in terms of hydrological parameters. Okay, so here we have this function K is the hydraulic conductivity function, C, which appears here, the coefficient of the time derivative of the pressure head is the specific moisture capacity. And since we want to address this issue in the context of irrigation, we shall also model the root water uptake, which in this case is the function R, that depends, of course, on the crop or plant that we're dealing with. And clearly, I mean, this describes the crop that we are using. K describes the soil, okay, we are focusing on. And well, as I said, we can consider this Richard equation either in explicit form when we consider the dynamics on H, or in implicit form when we consider the dynamics on theta, on the water context. So, as I said, this equation has been validated by, well, in several studies analyzing the percolation of water in soil. So this is usually the profile of the water content with respect to the pressure head, H. So clearly this is a nonlinear relation between these two quantities that, I mean, based on this kind of behavior, we try to determine which kind of hydraulic functions might be more meaningful. Okay. And in this direction, well, many different models have been proposed, starting from, well, some pioneering works that I mentioned here. So these are the possible hydraulic functions we can consider. Okay. So there is a Gardner model that takes into account an exponential relation between pressure heads and water contents, and that's the hydraulic conductivity function that results from this relation. Then we have other models known as the Aberkamp model and the Van Gennuten-Moalen models. So in this case, the relation between moisture and pressure head is given by a rational function, basically, with different parameters. So all these other parameters are somehow determined by the soil under consideration. Okay, so we will not focus on the value of the parameters, just to understand the kind of constitutive relationship we can consider between these functions. Okay, this quantity. Okay, so I said we want to use this dynamical system and study an optimization framework for this. Okay, so we want to consider the Richard equation. For simplicity, I will focus on a one-dimensional domain. Okay, so from 0 to Z, so that is going to be the depth of the soil under consideration. And clearly, in this system, our control enters as the irrigation module, okay, which is the top boundary condition. Okay, so here I've written the Richard equation in an implicit form. So with respect to the dynamics at theta, and the amount of irrigation we provide is our control input. Okay, the bottom boundary condition, the function G, describes the interaction with the environment below the part of the area of the soil we are interested in, which is usually where the roots of the crop are. And then, well, clearly we have some initial moisture, so initial condition that describes the initial water content in the soil. Okay. Now, for the root water uptake that that here enters as the source term here, we use a rather simplified model introduced by Fields, and where basically has this affine profile. Okay, so there is a region that's where the root water uptake is maximized. Okay, so there is a specific interval of pressures where the roots will have the highest water uptake, and well, and then there is a linear behavior. The slope depends on the evapotranspiration of the soil, so this is also related to other physical quantities of the model. And well, as I said, we are interested in the optimization constraint to the dynamical system provided by the Richards equation. So we need to introduce a utility function, okay, an objective function that describes what we want to either maximize or minimize. In this case, well, we have a twofold objective. On one hand, we want to optimize the root water uptake, right? So this can be a proxy for optimizing the yield of the field, for example. So we want the root water uptake to be as close as possible to the max value that can be achieved. And this is one objective. And then the second one, well, we want to achieve this while minimizing the irrigation cost. Okay, the cost of, well, the irrigation effort, if you want. Okay, and well, in these two objectives, so if you just want to optimize the irrigation cost, just set the irrigation to 0, but that will not improve our water uptake. And if you want to, well, get the pressure such that the root water uptake is maximized, this will have a irrigation cost associated. Okay, then we have a parameter lambda that can somehow tune which of the two objectives we want to prioritize. Okay, clearly we can only choose control actions that are admissible, and in this case, admissible controls needs to satisfy some physical parameters. So, for example, the control that is this time-dependent function, right, that we want to determine must be such that we never reach saturation. Okay, so here we are describing a quasi-unsaturated model. Okay, so we assume we are in a condition that we never reach saturation in our water content. Now, although this is a quadratic function, right? So this seems a relatively trivial optimization problem, because if it is a quadratic function, basically we have a parabola, right? So we always have one unique minimum, right? But actually, this is not the case in our problem, because although the functional j is quadratic, the nonlinearity of the equation, okay, so here we have the state h or theta is the same, the satisfy nonlinear dynamics. So this means that the optimization problem is non-convex. Okay, so you shall imagine a situation where if you look at the landscape of this cost function, you might have several local minima. Okay, and so we have local minimum that occurs in the optimal control problem. Now we want to understand how we can use control methodologies to describe and characterize these local minima.
We've got about 3 minutes left.
Yeah, okay. So this leads to introduce, well, the adjoint state. That is a classical method in control theory. And thanks to this adjoint state, we can characterize the optimality systems. So here these are all equations that we have seen already. So this is the direct problem, the Richards equation. This is the adjoint equation in black. And thanks to the adjoint state P, we can characterize the optimal control, that is this function U star, associated with the flux of the adjoint state at the top boundary condition. Okay, so this is, as I said, a very powerful control framework where we can get a characterization of the optimal control and then use this in applications. So that's what I want to show you in a couple of examples. The first one is a soil described by the other camp model. Okay, so these are again the hydraulic functions. And this is the Fields type model for the root water uptake that I already introduced before. And we have some, so we will use the parameters of a sandy soil. Okay, so with a relatively fast diffusion, okay, infiltration of water. The most is 35 centimeters per hour. And we will see this simulation for when that runs for 3 hours and with a depth of 70 centimeters. We have some initial and boundary conditions at the bottom, and then at the top, the condition is our optimal controls that we want to determine. And this is the profile of the optimal water content obtained through the optimal control that is determined here by the optimization algorithm. Okay, so as you can see, well, we are assuming here that is enough that the bottom condition does not reveal the action of the irrigation. So it's always the same. And then we can see here as the profile of the optimal water content reaches a certain state, okay, that is where the root water uptake is maximized. Okay, and we can see this also in a second example where we use instead Van Gunther-Moellen model that is convenient to describe low minifine sands. These parameters are taken from a soil in Berlino, New Mexico.
Sorry, if you could just maybe wrap up.
Yeah. So I'll just show the last simulations associated with this soil. So also in this case, we can determine an optimal control, okay, that well has a certain behavior and leads the water content to even to almost a steady state profile. Okay, now so this is what we have done, and what we plan on doing is to consider the same model, but to add also the presence of nutrients, so to describe also the dynamics of nutrients. In this case, of course, the model needs to be enlarged with also an equation for the dynamics of the nutrients. But we believe that's something that needs to be done in order to determine how we can minimize fertilizer consumption as well as water resources. Okay, so that's all, and thank you for your time.
Thanks a lot. Roberto, if you wouldn't mind coming up to the front, we're running a little behind, so we'll maybe take one question for each speaker and then in